Welcome everyone. So this video we're going to do single displacement reactions with metals and ionic compounds. Alright, unlike a double displacement where you see two ionic compounds in a single displacement, you only have one of them. Alright, so A will be a metal, B will be a metal cation, a metal that's lost electrons, and C is going to be some kind of anion. It doesn't usually participate in the reaction, unless we were doing a halide displacement or something like that, but that's not the focus of this video. All right, so what happens is you have a neutral metal, and it's neutral. I'm symbolizing that with a 0. And it's going to give electrons to the cation. When you give electrons to the cation, it used to have a positive charge on it. But at the end of the reaction, because it received electrons, it will have no charge on it. All right? So the old cation becomes the new metal. Whereas the old metal gave away electrons, it becomes your new cation. All right? And there's C. C is often like a spectator ion, or it's not really doing much. It just stays negatively charged the whole time. But important for this reaction, B is no longer to maintain its ionic bonds with the C minus because it's now neutral. You need plus and minus to connect together. But A, now being positive, is able to form those ionic bonds. All right. And as to what sort of subscripts we make, that's going to be based off the periodic table and the charges we see there. And we'll do that through example. All right, so how do you know if a reaction happened? This is something called the activity series, or maybe some people call it the reactivity series. All right, it's a little bit intimidating, a figure to look at first, so let me explain what's going on. We have a list from top to bottom of the likelihood of an element giving away electrons. Okay, so everything at the top here, like we say, beta reducing agent. So as we go towards the top, here, beta reducing agent, lithium on down, starting with lithium. Lithium, out of all the elements listed, is the best at giving away electrons. Okay. So as we go further down the list, that means they're going to become worse at giving away electrons. But if you're bad at giving away electrons, I'll just make sure that word continued was in the shot. If you're bad at giving away electrons, that means the opposite is true. That means you're good at receiving electrons. All right, so gold is really good at receiving electrons. Said another way, gold is good at being a neutral element. Okay. So this is the activity series, and in order to predict that electrons will be transferred in a single displacement reaction, we are looking for this. We are looking for the element A to be above wherever B is on the symbol. All right. Oh wait, I meant to circle this. A is above B on the reactivity series. This is why I like to write my single displacement reactions in this order. I like to write the lone element first, and then the ionic compound second. That way it's very easy for me to do this comparison and make sure this A is above whatever the B is. In fact, if I were given a problem and they listed the ionic compound first, I will rewrite and rearrange the problem just so that my brain can think in this order I'm very used to working in. All right, so this is the way I wrote out the reactivity series. There's other places you can find this. I pulled this from Chem LibreText. Let me show you that link. Okay, here's a Chem LibreText. I'll put the URL in the description. And they talk about some halide replacement as well. Again, that's not the focus of this video. I'm looking at this activity series right here. Okay. I'm hoping some of this can be a little bit rooted in common sense, if that's like possible. I know for many people this is their first chemistry course, but like if we relate to common experience, you know, something that hopefully you learn in lab is don't put plain sodium into water because it's dangerous. It's very reactive. We have all these reactive elements going towards the top. Potassium is very reactive. Calcium metal, you put in water, it'll start fizzing hydrogen gas immediately. But again, I understand that's not everyone's experience. Iron's kind of in the middle here, and we know that iron can rust in the right conditions. But as you go down, we have less reactive metals. Copper is known for not being a very reactive metal. I mean, yeah, the Statue of Liberty for the United States, it is covered in a green patina, but that's because it's really close to the ocean, right? But copper, like, it can be found in nature as the elemental metal, kind of evidence of it not being overly reactive. And when we get really close to the bottom here, you have metals like platinum and like gold, which are very well known for their lack of reactivity, leading to many desirable properties. Okay, for example, if you were to stick your hand into water, you know, salty water like in the ocean, you're wearing a gold ring. Hopefully it's a good fit, but it's not going to dissolve in the ocean water because gold is not as reactive as sodium. Okay, so we're going to use the locations on this reactivity series to predict reactions, whether they happen or not. Example 1. So I talked about how come your gold ring doesn't dissolve in the salt water. Well, we can look at this from the point of view of doing a reaction. All right, so let's look for the first element, gold. And gold's the very bottom, so we might see where this answer is going already. And sodium is above gold. I ran out of space, so our figure goes like that. So sodium is above, not the other way around. We need AU above an A, the first one above the second one for a reaction. RxN is shorthand for reaction. But it's not. So therefore, students love getting these problems because there's no work to do. There's nothing to balance because nothing is going to happen. All right, no reaction. For those who've heard of the term electrochemistry, this is just basically a table of electrochemistry. That is to say, do electrons spontaneously get transferred or not? For those who like physics words, the key word is voltage. If the element is above the cation, then you have a positive voltage, which means electrons move spontaneously. That's how batteries work. There's a selection of chemicals in there where when a circuit is complete, the electrons will spontaneously move. That's because part of the battery has a metal that's above the cation somewhere in this electrochemistry series here. Okay, so that's example 1, no reaction. All right, example number 2. Here's a fun one. We're not going to be in water this time. We're going to talk about the thermite reaction. All right. So thermite involves a metal oxide of some kind. There's aluminum and iron involved, and one of the metals is an oxide. All right. So let's come up with some reactions here. We could try adding elemental aluminum and adding it to iron 3 oxide as a powdered solid. Okay, I said iron 3 oxide. If you're wondering if I made a typo or not here, then I would invite this to be a good time to review naming rules. The long story short, iron's a 3+ charge here, which is why I say iron 3 oxide. It has nothing to do with the subscript. All right, and we're going to wonder if this reaction takes place. And I'll put little verses here. We're going to compare the reverse situation. What if we had elemental iron being mixed with powdered Al2O3, aluminum oxide. All right, comes in the mineral form of alumina. All right, this is the mineral form of, this is available as the mineral hematite. So only one of these reactions can go. There's only one way logically this can go. You know, if this is above that, then the opposite must be true here. Okay, or maybe this one's above that, then the opposite would be true. All right, enough talk. Let's just consult the reactivity series. All right, so here's aluminum, and there's iron. All right, so whatever reaction where I wrote aluminum as the element by itself, the first thing, then that will have a reaction. All right, so let's just do the easy part first. This has no reaction. Iron's below aluminum, so that's not going to be a reaction. All right, now this one does have a reaction, so we're going to have to figure out how to get the products. All right, first off, you could do the easy part first if you wanted to. Iron's going to be by itself. And for metals, there's no subscripts. It's not like oxygen or hydrogen where you have to put a 2. Metals, you just write it by itself. Okay, so got that part done. And now we know the only things left is aluminum and oxygen. Aluminum gave its electrons to iron. It's going to be our new positive charge. Oxygen stays negative, so we have to just figure out in what ratio aluminum and oxygen mix. Okay, so this is where the periodic table comes in, and you consider all your charges. All right, we don't have any polyatomic ions here, so we can just stick with the periodic table. 1 plus, 2 plus, 3 plus, 4 plus, 3 minus, 2 minus, 1 minus, 0. All right, so aluminum's in that 3 plus column, and then we have oxygen in the 2 minus. So we have aluminum and oxygen needing to mix in a 2 to 3 ratio. That's how we're going to get to that least common multiple of 6. In plain language, that's how we get the charges to balance. Okay. So here, just to recap, we have aluminum 3 plus, O2 minus. 2 aluminums gets us to 6 plus. 3 oxides gets us to 6 minus. 6 plus, 6 minus evens, or you can just do a crossover method. Al2O3. So that will be our answer for that product. Okay, and the last thing to do, we checked if it was possible. We checked if we checked what the product should be. Now we just have to make sure the equation's balanced. All right, so I ended with 2 aluminums. I must start with 2 aluminums. I started with 2 irons. I must end with 2 irons, and my oxygens 3 and 3. So that was pretty convenient. Okay. All right, so there was example 2. Again, if there's no reaction, my understanding is there's no point in trying to balance an equation if nothing happens. So I don't think it's, I mean, you could balance the reaction if you wanted to, if you were to find some weird set of reaction conditions to force it to happen, but that's not really my concern. That's not the focus of a 101 course, typically. Just say no reaction. All right, last example. All right, just kind of save time here. This one, I already predicted the products for you. Copper can be 2 plus or 1 plus, but here I have it as a 2 plus. We have copper, metal being put into a silver nitrate solution, and then we're getting this product, these products, okay? And we see that copper is above silver, so this reaction will go. What we're going to do here this time is we're going to analyze this from the perspective of making a net ionic equation. All right, so the first thing I want to do is balance this equation. We end with 2 nitrates, so we must start with 2 nitrates. We have 2 silvers here, so I must end with 2 silvers. And this is our balanced molecular equation. All right, if you want to review net ionic equations or get a start on that, I would recommend, I have a video about double displacement reactions where I talk about net ionic equations, so feel free to consult that or any other reference. All right, so that's our molecular equation, and then we're going to make a total ionic equation. Anything aqueous will be broken apart into ions. So I like to circle any solids, liquids, or gases, so I know not to dissociate those. So that's aqueous, I'll go ahead and dissociate them. All right, so, but these I can just bring on down. We have copper solid, 2, Ag plus, aqueous, 2 nitrates, all right, copper 2 nitrate, so that we're going to have copper 2 plus, aqueous, plus 2NO3 minus, aqueous. Done with that, and then we bring that down. To silver metal atoms. Again, circle any solid, liquids, or gases when you're doing net ionic equations or total ionic equations. That's what I like to do. And then we're going to look for any spectators. Okay, spectators are aqueous on both sides of the equation, any spectator ions. They're watching the reaction. They're not actually participating in the reaction. All right, we have 2 nitrates on each side, so that can go away. That can go away. We don't call copper a spectator because here it's neutral, here it's 2 plus. If even one thing about it is different, then you cannot eliminate it. All right. Same thing goes for silver cation here versus silver element here. All right. So that means this survives, that survives, that survives, that survives when we're making our net ionic equation, which is the same as the total ionic equation except no spectators. So here it is. In this reaction, we have a single copper atom and 2 silver cations. Copper gives away 2 electrons. There's 2 different silvers to accept 1 electron each, leaving us with 1 copper ion and 2 silver atoms. All right. This is a pretty fun reaction to do in the lab. A little bit expensive because you have to buy silver nitrate, which is not cheap, but you do this reaction in the lab, you'll see as you add the copper and give it a little bit of time, the solution gets more and more blue from the blue copper ions in water, and you have these nice silver crystals growing off of your copper. Okay, I think that's enough for this video, and let me know if you have any questions or suggestions. All right, thanks. Take care.